Okay, thank you for the kind introduction. So my name is Lars. I'm from NTNU in Norway, Trondheim. This work has been done in collaboration with my colleagues, David Morin and Sture Hopperstad, who I have to acknowledge. So it's micromechanics-based modeling of porous ductile solids with non-uniform void size distributions. And the background and motivation for this work is that typically in aluminum alloys and in other type of metal alloys as well, but we work a lot with aluminum, the particle sizes, they typically follow a log normal size distribution. This type of unit cell simulations, they are based on a single void size, basically. So there's no distinction or there's no size distribution. So we want to look at the effects of that, the consequences for modeling. I mean, how can we include this in a model? Typically, you need hundreds, thousands of particles to actually draw a representative sample from this particle size distribution. So the question is, how can we do that and attempt to do that? So what we have done is to run a lot of numerical simulations using so-called SVEs, so statistical volume elements, where we have lots of voids of various size. These void sizes are sampled from the log normal size distribution. And the main purpose of this study is to compare these two approaches, where we use either spatially resolved voids or a very efficient model with homogenized voids. Okay? And then we run simulations with different sample sizes, and we draw 30 different SVEs or 30 different samples from the size distribution for each sample size. Okay, so the assumptions we rely on here are, that we have pre-existing voids that we sample from this log normal size distribution. They're equally spaced, so we have a uniform spatial distribution. Then we can divide our model into equal sized subregions containing a single void, a spherical void in 3D, but here it's a circle. And then we do the same, but we distribute porosity in the case of homogeneous. So we use 2D models here to be able to run simulations with discrete voids, with a lot of voids. Okay, so this is the procedure to distribute the void sizes. It's quite straightforward. We select the distribution parameters and an initial average porosity. Then we sample n square number of voids, various sizes, distribute them, compute the total void area, total cell area, so that we get the average porosity we want. And then we partition it into n by n subregions and assign these local void sizes or porosities. So this is just a sort of a sketch of the finite elements we use, models we use. So they're in plane strain. They're subjected to in-plane periodic boundary conditions. We assign constant in-plane stress ratios. So this is basically how, or monotonic loading, but we can't really control out-of-plane stresses. So this is just becomes what it wants to become. The stress states we impose are 3 different types of normal stress states. So the major or the principal loading direction here is x2. And then we have 3 normal stress states where we assign a ratio of 0, so plane strain tension, 0.25 or 0.5 of this lateral stress. We also have shared stress state, but I will not discuss that here because we don't have time. So only look at the normal stress state results. Okay, for a constitutive model, it's very simple. J2 flow theory. with the flow stress given here. So it's just basically a 3-term vote rule with also a linear hardening at the end to have some numerical stability. These are the material parameters. They are representative for some 6000 series aluminum alloys. And when we have homogenized voids, we use the Gerson model. Okay, and in that case, these are the parameters, the GTM parameters, Q1 and Q2. Okay, so the void size parameters or the distribution parameters and the average porosity we used are listed up there. We looked at 4 different sample sizes, 3 by 3, 5 by 5, 10 by 10, and 22 by 22. So the last one is actually the number of voids you need in 3D. So if you have 22 by 22 by 22, you get around 10,000 voids. And that is roughly the number you need to get a statistically representative draw from the size distribution. So this is some kind of a cross-section of that 3D model. And then for each of these sample sizes, we generate 30 SVEs. So this is basically a unique model, 30 draws. And so this gives 120 simulations for each modeling approach per stress test. There's a lot of simulations, basically. Okay, yeah, there's a lot of results because there's a lot of simulations. So I will not go into the details, but of course you can appreciate that there is a lot of scatter in terms of stress strain, porosity against strain, both for discrete voids and for homogenized voids. Okay, that's the main message from these results. So if we look at, for instance, these stress states here, so a lateral stress ratio of 0.25, just to show you something, we see that up to a moderate level of plastic deformation, there is basically no influence of this heterogeneity, meaning that you could run a unit cell and get the same result. But when you pass the peak and go into the softening domain, you have lots of differences. The failure strain will vary significantly between the different draws for a given sample size. And of course, also for different sample sizes. And in general, we see that if you draw more voids, you have a larger sample, you will get earlier softening and earlier failure. So this unit cell model with a single void will be an upper bound type of approximation. Okay. Now for the failure strain, we can see that it will decrease on average if you increase the sample size. And also, it seems that the scatter is less when you draw more voids, which is also intuitively makes sense. So, and another thing is that qualitatively speaking, the 2 types of approaches give the same results, right? So if you discretize the voids, you have millions of elements, or you have just a few elements using homogenized voids, you get more or less the same type of results. This is just to show you the complexity of these localization bands when you have more voids, and also to show you that there is some similarity between simulations with discrete voids and homogenized voids. So they give similar type of localization patterns and bands, which is very important if they're going to give the same type of results, right? So you have these localization bands and they're well reflected by this homogenized void approach. So if we compare these 2 models more directly, you can see that at least for these porous plasticity parameters, the homogenized void models, they will always give a higher failure strain. Of course, you could tune the parameters differently to lower these curves, but they give higher failure strain in this case, but they give the same trends, right? And this you can see in the correlation here between failure strain for the homogenized voids along the x-axis and the failure strain for the discrete voids on the y-axis. You can see that they correlate pretty well, which is good because then we can use this homogenized approach to get the same type of results and predictions. Okay. And another factor is that the speed up is, of course, tremendous if you use homogenized voids. So there is a factor of over 3,000 for the largest sample size. And the speed up increases with the sample size. So with the discrete voids, we spent 240 days computational time. With the homogenized voids, we spent less than 3 hours. So it was really, really efficient. Okay, so with this, I would like to conclude. And basically what I wanted to show was simulations using these two types of approaches to include non-uniform void sizes in this type of models. Yeah, and that's about as far as I come. Yeah, thanks. So the key results are basically that up to peak stress, you don't see any significant effects of these non-uniform void sizes. So you could basically just use a unit cell to give the same type of results. But for the failure strain, there is a large degree of scatter, which tends to decrease on average with an increasing population of voids. And considering the significant speed up and the good correlation between the homogenized modeling approach and these discrete voids, we think that this homogenized approach could be good to use in future. Maybe we could plug in some more refined type of porous plasticity models and so on to look at other things. But for now, I think it demonstrates the applicability of this approach. All right, so that's what I had to say. Thank you for coming.